when we run ckpt, well, ckpt now becomes the file that we've loaded into memory, which has a dictionary, best fitness none, model, detection model, EMA for exponential moving average, and that got allocated to the CPU. Now here, within the ckpt dictionary, we're calling EMA, but given that is set to none, we will call the model, which is right here. ckpt model is a detection model, and it has all these different values. We have the hyperparameters defined here. We have model, which has different layers in the neural net. You can see we have 25 layers. The different layers can be also seen here, these being layer 0, 1, 2, 3, and so forth. 0, conv, 1, conv, 2, C3, etc. We also see the names of the different classes. Our class will be 2 for car. The number of classes, 80. There are 80 potential classes that the neural net will try to predict. The number of layers that need to be saved because they're going to be used downstream by the neural net. The stride, in this case, 8, 16, and 32. Training false, and then the YAML file, which has some additional information. The YAML file can be also found here. YOLOv5l YAML. In our case, information was already stored in our YOLOv5l.pt, but here you can see that the values defined here correspond to the number of classes, some multipliers, which in our case are 1, so we don't have to worry about them. And this is related to the model, so YOLOv5l has a multipliers of 1. The anchors indicates that there are 3 layers, 1, 2, and 3 layers, and each layer has 3 anchors, so width and height, and width and height for the third anchor in that first layer, and same for the other anchors in the other layers. The number 8 means a stride of 8. If we go back to our diagram, you can see that the image that is fed to the neural net is 640 by 640 by 3. That image gets downsampled, in this case by half and then by half again. By half again here, one more time, all the way to 20 by 20. And these are the number of channels. So the image went from 640 by 640 to 20 by 20. These 20 by 20, these dimensions are actually maintained for one of the 3 predictions of the neural net. There will be a 20 by 20 grid prediction, a 40 by 40, which is the 20 by 20 upsampled, concatenated, and then the result of that will be 40 by 40 grid. And then here, we will also have an 80 by 80 grid. So 3 predictions in total. If you notice, the input image, 640 by 640, gets downsampled, in this case, by a factor of 8. So 80 by 8, 640, which is what this stride means. You could see it as the input image has been strided. In this case, 40 by 40, that means that the image has been downsampled by a factor of 16. 40 times 16 is 640. And here, by a factor of 32. 20 by 32 is 640. This is what these values mean here. We also see the backbone. You can see here the legend from number, module, and arguments. -1 means that the input of this layer is the output of the previous layer. So in this case, -1, we're just getting the input image, but that's the only input to this convolutional layer. We're only going to perform it once, and the module we're going to call is conv. These are classes that are defined in common.py, which we'll go over it as well. And these are the arguments, 64 by 6 by 2 by 2, which correspond to the channels. In this case, the input channels of this layer are 3. The output channels are 64. And in order to have a 320 by 320 by 64, we need to apply a kernel size, a patch that goes through the image of 6 by 6, and then a stride of 2 and padding of 2. We'll talk about these values in more detail as we go through, but this is what this means. And this is layer 0, index 0. In a similar fashion with this one, for example, let's go and look at this one. Again, this one, the input is the previous layer. So C3, the previous layer is the input. And here, this means that in this C3, in this particular case, there is a bottleneck type 1, which is right here, which is going to be executed 3 times in sequence. So in this case, the tensor will feed into the C3 module, and it will perform a convolutional layer here and also here. This one will feed into a bottleneck type 1. So the tensor will flow this way, perform a convolutional layer, and then another convolutional layer. We will add the residual path to that, and then again perform it another time and add the residual path, and then a third time perform the convolutional layer and this convolutional layer as well, the residual path, and then that output gets concatenated with this operation, this layer here, which then gets convoluted as well before sending the output to the next module. Here, for example, by the way, we have comps, C3s, and SPPFs, which you can see here at the bottom, consists of convolutional layers as well as max pooling layers. That's what's called the backbone. When the image starts to upsample, that's what we consider to be the head. In this case, the 20 by 20 by 1024 tensor will be upsampled. In this case, you can see that this one, for example, there is a module here that gets the input from the previous layer as well as from index 6. So we can look at that one, and this is this one in this case. We see that 0, 1, 2, 3, 4, 5, 6. The output of 6, in addition to going downstream, it also goes into the head. See that the dimensions are the same, 40 by 40 from both paths. That's how it can be concatenated. So that's what the input in this case is. There are other concatenates as well. And then another special case here is the last layer, which takes input from module 17, 20, and 23, which are these ones right here. 17, this is module 17, and that is one of the inputs into the detect class. You can see here. The module 20 and 23 are also inputs into the detect. So that is 17, 18, 19, 20. The 20th module also is an input. And then 21st, 22nd, and 23rd. So the modules 17, 20, and 23 are inputs into the detect class, as we'll see in much more detail. Let's go back to where we call it from. Now here, given that this is none, we're gonna step into this, and ckpt model will be the detection model.